Can we say more? Well, in general, not. Anything can happen here on the circle, and anything can happen also for the eigenvalue R of A. There may be other eigenvectors which do not have a sign, which are not positive and not negative, which change signs. But this can also only happen if somehow we have an eigenspace for the eigenvalue R of A, which is at least two-dimensional, and then we can maybe have linear combinations of positive eigenvectors, which may then change signs. But we say that a positive matrix A, necessarily a real, but it's positive, all entries are positive, is irreducible Well, the word irreducible is used in several contexts, but here it's in the category of positive ordered spaces, of ordered spaces and of positive vectors and positive matrices, if it leaves no other ideal than the trivial ideal, the smallest vector subspace of Cn, and the largest one invariant. So here's the word ideal which appears. So an ideal is, first of all, it's a vector subspace of C to the n. It has also an order structure, so the intersection with the positive cone is non-empty, and somehow if some positive vector is in this ideal and I find another vector in Cn such that the absolute value of this vector is smaller than the vector in the ideal, then the smaller vector, or actually the absolute value, which we have taken one, this other vector is also in the ideal. So actually in Cn there are not so many ideals. The ideals in Cn are of this form. Well, they might have in one component a 0, and then might have some components which are all of C. Well, let's say the first and the fourth component are 0 and all the others are non-zero. That are the ideals in Cn. And saying that such an ideal is invariant under the matrix, it means that if I take an element of such an ideal and apply A, then the result is again in this ideal. So these are irreducible matrices, and one definition given here. For irreducible matrices, we can say the following. Let A be irreducible. In particular, it is also positive. We only call positive matrices possibly irreducible. Then spectral radius is strictly positive. And the eigenspace corresponding to the special eigenvalue is one-dimensional and spanned by a strictly positive eigenvector. So strictly positive, I recall that all components are strictly greater than 0. Also, this is new information. It may be that the spectral radius of a positive matrix is equal to 0. For example, if the matrix A is equal to 0, then the only eigenvalue is 0, and then the spectral radius is equal to 0. But there are also non-zero positive matrices which have spectral radius equal to 0. For example, the matrix, this Jordan block, all entries are greater or equal than 0, but this Jordan block has spectrum only 0, and therefore the spectral radius is equal to 0. But this matrix here is not irreducible. It leaves the space which is in the first component C and in the second component 0. So this one-dimensional subspace of C2 invariant, and that ideal is different from the trivial two ideals. So that matrix is not irreducible, but it would also follow then from this theorem. The proof, well, I will not prove possibly this assertion A, but I will prove this assertion B. So A is without proof. So let X in Cn or Rn actually be a positive eigenvector of A for the eigenvalue R of A, spectral radius, and we already know that there is a positive eigenvector. Now, this positive eigenvector can be strictly positive. Then we are already find that there is at least one strictly positive eigenvector. But if, and let's call this X, if xi is equal to 0 for some I between 1 and n, at least one component is 0, then the ideal, well, here only C's, but then 1, 0, So this is the ith component. Is invariant under A. And well, this has to be shown by positivity, but if you take some vector in here, which is in the ith component zero, and well, then you have to show that even A applied to this vector is in the ith component equal to 0, and there you use the positivity of the matrix and the positivity of this vector. So this is an exercise. I leave it as an exercise, but a contradiction. That's a contradiction here to the fact that A is irreducible. Hence, this cannot appear that some component is 0, and therefore the eigenvector is strictly positive. So here x is strictly positive. Now let x be any eigenvector. X in Cn, or actually Rn, be any eigenvector of A for the eigenvalue R of A. Then, when I take R of A and I take the vector x, but all components, I take the new vector which has components only consisting of the absolute values of the components of this one. So I call this the absolute value of x. This is, since R of A is greater or equal to 0, I can put this inside, and x is an eigenvector, so this is Ax. And now when I write this out, this is smaller than actually the matrix, which consists only, well, of the absolute value of A, but A is positive, so this is A times this vector x bar. Okay, that is A minus R of A times identity, and here I take this vector, that's positive. Let x bar be an a positive eigenvector of the transpose of A, or actually I should say the adjoint of A, but A is a real matrix, so I can say the transpose since the transpose is also irreducible, and also this is an exercise here, it follows that x prime is strictly positive by this argument we had already here above. And therefore, all components here are strictly positive. All components of this vector here are positive. So it means when I take the inner product of this vector and a minus absolute value, so I sum up actually only positive, so the components of this one times the components of this one, and then the sum over all components, all, even here the terms here are positive, the summands are positive, and the sum is then actually positive. And this is equal to x bar, and here's a x minus x r of a x, so by the additivity of the inner product. And here, this matrix I can put to the other side. Then I have the transpose. And x prime is a positive eigenvector of this transpose. So this is actually equal to r of a x prime x minus r of a inner product x prime x, and this is equal to 0. So we have started with something which is positive, but actually have an estimate for also from above, from the other side, that's equal to 0. And therefore, this here is equal to 0, but let me just recall, this is the sum over I equal to from 1 to n of the ith component here, and the ith component of this vector here. But this vector here is strictly positive, so all these factors here are strictly positive. Nevertheless, this sum here is equal to 0, which means that all the components here must be equal to 0. Because if one of them, since this vector is positive, would be strictly positive, then the sum cannot be 0. So we obtain from this chain here that actually this vector here is equal to 0, which means if x is an eigenvector, then also the absolute value of x is an eigenvector. Eigenvector of A for the eigenvalue R of A. But now, if x is an eigenvector and the absolute value of x of this, then also this here is also an eigenvector. And actually, this here is an eigenvector of A for the same eigenvalue. But now, if some component, so of course I take the sum here component-wise, if some component here is negative, then I have some negative component plus the absolute value. That's 0. So negative components, strictly negative components are here turned into 0. And if this is positive, then also I have here that doesn't change the component, so the component remains unchanged. And I call this the positive part of the vector. That's an eigenvector, and actually it's a positive eigenvector of the matrix A for the eigenvalue R of A. And now there are two possibilities. Either x plus is 0, okay, then maybe all components here are less or equal than 0, or that's really a non-zero vector, but if it's a non-zero vector, it's really an eigenvector, and then x plus is strictly positive. In that case, somehow all components of x were already strictly positive, because then x is equal to x plus. So that means x is strictly positive because it's equal to x plus, and this means x is less or equal than 0. But then, in that case, minus x is greater than 0. It's, of course, also an eigenvector, and maybe it means that just x is 0, or x is strictly negative, which means that all components are strictly negative. So in that case, minus x is strictly positive. So any eigenvector of A is either strictly positive or strictly negative. And then now, if imagine that the eigenspace would be at least two-dimensional or higher dimensional, then we find several eigenvectors, and which are linearly independent. And if they are linearly independent, I can take a linear combination of two such vectors, which are non-zero, such that the linear combination is non-zero, but it is 0 at least in one component. And 0 at least in one component doesn't work. That means that actually 0 in one component means that we already in this case, then the linear combination is 0. This is not possible. And therefore, we find that eigenspace is one-dimensional and it is spanned by a strictly positive eigenvector. Let me just add to the above theorem on irreducible matrices that more can be said. Actually, the spectrum on the circle with radius r of A is, at least if you normalize it so that the spectral radius is equal to 1, a multiplicative subgroup of the complex numbers. And the eigenspaces corresponding to such eigenvalues on this circle are all one-dimensional. This can be even strengthened if you consider a yet smaller class of strictly positive matrices, actually strictly positive matrices where all entries are strictly positive real numbers, are all irreducible, but for such matrices, actually the spectral radius is the only eigenvalue on the circle with radius r of a. All other eigenvalues have smaller absolute value. They lie in the open disk with that radius r of a. But I don't want to go into detail in that direction. I just want to mention briefly one application of the theory of positive matrices, and that's Leontief's input-output model, in which we consider a national economy, and this national economy is divided into several economic sectors, and each sector produces one good. So n sectors and economic sectors produce n goods. For example, cars or wood or clothes or whatever. And in order, now we look at such an economy over a certain time period, for example 1 year, and we look at the production of this economy. So what is the final output? So in order to produce xj units of the jth good, so in order to produce cars, maybe you need many other goods from other sectors, and the more you want to produce, the more you need from other sectors. One needs aij times xj units of the ith good. So there's an assumption that there's a linear relation. The more units you want to produce of xj, of the jth good, the more units you need of the ith good, and there's a linear dependence. That's of course an assumption, and of course this is the total output here at the end of the year. The demand or net output at the end of a time period, at the end of 1 year, is, so di, that's the number of units you have really for free, or which you can sell and for which you can do anything at the end of 1 year. That's the gross output, the number of units you have produced of the ith good, but then you have to subtract everything you needed for the other goods. So, and actually this is then a sum from j equal 1 to n aij xj, and maybe you need also some units from the same good in order to produce this good. Maybe you need some cars in order to produce cars. And here somehow this demand vector, the demand vector which is given, that's what you want to have at the end, is positive, as well as the matrix A So this linear relation, in order to produce some units of the jth good, you need really a positive number of the ith good, and this part number here is positive, then also the aij is positive, and the total output x, which is this vector here. This relation here is equivalent, or it can be rewritten as the identity matrix applied to x minus, and this is the matrix product, A times x. This is the output vector, the demand vector D. Now, maybe you want to have several possibilities of positive demand vectors. The question arises now, you know this vector, is the matrix identity minus A is invertible? And moreover, for positive demands, you want to have positive total outputs. Is so it maps, does the inverse map positive vectors to positive vectors? In other words, is the inverse positive? And the answer to this question is actually given here. And therefore, we have the following corollary. The following are equivalent. So identity minus A is invertible, and the inverse is positive. This is equivalent by applying this equivalence down here with lambda equal to 1, that the spectral radius is less than 1. And this can be computed, and then we call such a matrix A productive. So productive matrix is by this corollary the same as saying that the spectral radius is less than 1. Actually, one can prove, and one direction is easy, that this is still equivalent to saying that there's a positive vector x such that identity minus A times x is strictly positive. Well, actually, if you have this first assertion true, then you would just choose any strictly positive vector D, and you would apply the inverse identity minus A. You get something positive, and you get this relation that this is equal to D, which you have chosen to be strictly positive. So from 1 to 3, the implication is very easy. From 3 to 1 is not so short, but it's also not very difficult to prove this corollary. So that's one application. Actually, Leontief's theory of the input-output model is not so short. There are more aspects. You can also study economies. What do they do after 1 year, 2 years, and iterate, and see that if you somehow let your economy freely evolve, so what is the output after several years? I should mention, although this looks very simple and the theory of positive matrices or irreducible matrices applies very quickly to this model, that Leontief got the Nobel Prize of economics in 1973 for this model. And one should also mention that somehow the theory of ordered vector spaces, and not only of Cn but also of infinite dimensional ordered vector spaces, was introduced in the 1930s by Kantorowicz. And also he got a Nobel Prize in economics in the 1970s. I think it was 1976. An ordered vector space, maybe which you might know, is the space of continuous functions on an interval, and the function, so this is not only a vector space, a function is positive if it takes positive values everywhere. And then on such spaces you can again study positive linear operations which map positive functions to positive functions and study their relation. This has also applications not only in economics but also in the theory of partial differential equations, where you have the Laplace operator. The Laplace operator itself, in one dimension, it's just the second derivative. It's not a positive operator. You may have positive functions for which the second derivative is not positive. But the inverse of the Laplace operator, that's a positive operator. And for this operator on an infinite dimensional space, like a space of continuous functions, you can apply generalizations of one of the two theorems above, and you find out by different theory of self-adjoint linear operators on Hilbert space that the spectrum of the Laplace operator is just consists of real eigenvalues which tend to infinity. So if you take minus Laplace operator, the spectrum is really positive, and you have infinitely many eigenvalues, but the first eigenvalue has an eigenfunction which is positive, and that's also a consequence of the theorem here, or in addition then here, depending on where you consider the Laplace operator and which domain. Of course, positivity plays also a role in the evolution of heat. So there you have a parabolic equation, the heat equation, and physically it makes sense that if you have at time t equals 0 a positive heat distribution here in the room, or temperature distribution, that at any positive time the heat distribution stays positive, that heat doesn't become negative or temperature doesn't become negative from alone. I should lastly mention, but I will not go into details, that initially the Google algorithm for finding good answers to queries on Google used also positive matrices and their eigenvalues. And there are many more applications, even in finite dimensions, of positive matrices. That was all for this, I wanted to say, for this refresher course on positive matrices. I thank you very much for listening. I wish you all the best and say goodbye and stay positive.